rational equations today. These are equations that have fractions in them because that's what a rational expression is. And before we get into the whole solving piece, I just want to put up a reminder about something that happens in Algebra 2. It's called extraneous solution, and that will happen again in this chapter. Extraneous solutions are solutions that are not necessarily wrong, but they are false. And so you may or may not write down the second bullet point. We have this in our notes from other chapters on extraneous solutions. The second bullet point is just describing the fact that when you get an extraneous solution, you have done everything right when you're solving for x. So your answer for x is the right answer. But when you plug it back in, it doesn't work. The most recent experience we've had with extraneous solution is with logarithm equations. So we would solve logarithm equations, and sometimes we would get x values that when we plugged them back into the equation, they made what was behind the log a negative number. Well, we can't take logs of negative numbers, so those answers were undefined, and we did not have solutions. In this chapter, we're working with fractions. If you think about fractions and rules, we have one rule with fractions that says you cannot divide by 0. Never have, never will. We've said this numerous times as well. And so our extraneous solutions will show up anytime we find an x, we plug the x back into the equation, and it makes one or both or more of the denominators equal to 0. Okay, so that is an extraneous solution in Chapter 7. Checking for extraneous solutions is not the same thing as checking for accurate solutions. Okay, this is just checking to see, like, assuming we did everything right, if we plug this number back in, we get some kind of answer that's undefined. And in math, undefined answers aren't really answers. They aren't really solutions. The majority of your problems won't be extraneous, but just be on the lookout for it. Okay. Now, the type of fractions the type of equations we're gonna look at today are equations that are set up so you have a fraction equal to a fraction. Okay, remember, the whole concept of Chapter 7 revolves around fractions, rational expressions. You have actually already solved these types of equations. I will put an example on the board. I'll just make one up. X over 6 equals 7 over 15. That's a fraction equal to another fraction. You would tell me to solve that how? Cross multiply. So what are we doing today when we have a fraction equal to a fraction? We are cross multiplying. Now, ours may be a little bit more complex. Instead of having just like a single variable there, we might have like an x plus 3 or something like that. Okay, we might end up with some quadratics, so we might need to solve by factoring. After you cross multiply, solve for x. And then, of course, we talked about that last slide. Once you get x answers, plug them back in. Check to make sure your denominator does not equal 0. You do, yeah, you really do want it to work out. But sometimes it won't. Sometimes you'll plug x in, and it will make the denominator equal 0. Like if your denominator was x plus 4, and then you get x equals negative 4, that can't be a real solution, because negative 4 plus 4 would be 0 in the denominator, which is undefined. You do, I'd say, I don't want extraneous solutions. I want a solution that really works. Okay. I'm going to do an example, then you're going to do an example, then we're going to do a word problem, and then we'll have some work time. Okay, so here's the example I'm going to do. 7 over x plus 3 equals x over 4. When I look at that, I see a single fraction equal to another fraction. Some of you might call that a proportion. Okay, a ratio equal to another ratio. And I solve proportions by cross multiplying. So when I cross multiply, I'm going to do x times x plus 3. I'm going to write a little note up here for myself. Don't forget to distribute. That x is multiplying by all of x plus 3. So I'm going to do x times x and get x squared. And then I'm going to do x times 3, which is 3x. Be careful. Make sure you distribute to that second term. When you guys do your example, I'm going to come around like I do and peer over your shoulder. And I'm going to check to make sure that you've distributed to both terms. Okay. Then I'll cross multiply 7 times 4, which gives me 28. And in between those two is an equal sign. Okay. You never get rid of your equal sign when you cross multiply. Most common mistake for people when cross multiplying is to turn that into a fraction. Some people cross multiply and they write x squared plus 3x over 28. You just made your equal sign disappear. There is no equal sign. So remember that those things don't make a fraction, they're set equal to each other. Okay. Now I do have one issue here. In my equation, I have an x squared and an x. If you have x squared and x, get one side equal to 0. And factor. We have talked about since semester 1, chapter 3, really. If you have x squared and x, no amount of reverse PEMDAS, adding and subtracting, multiplying and dividing from both sides, is going to get x all by itself, because there's two different kinds of x's. So really your only option in this particular case is to make one side equal 0 and factor. So I'm going to subtract 28 from both sides, giving me x squared plus 3x minus 28 equals 0. And now I have a trinomial, and I can see if that factors. I have factors of negative 28 that add to make 3. 7 and 4, if I use a positive 7 and a minus 4. 7 times negative 4 will be negative 28. 7 plus negative 4 will be positive 3 in the middle. Set your factors equal to 0, so x plus 7 equals 0, and x minus 4 equals 0. And then to solve, I would actually have a negative 7 for my solution, and a positive 4. So be careful there. The numbers that you choose for factoring, like 7 and negative 4, your solutions will actually be the opposite of those. Negative 7 and positive 4. Now, I have two answers for x. What should I do with those? See if either one is extraneous, and you're not guaranteed an extraneous solution. If I take negative 7 and I plug it in for x in this denominator, negative 7 plus 3, does that equal 0? No, and I don't have to worry about the denominator on the right side, that's 4. Now try 4. 4 plus 3, does that equal 0? No. So is either one extraneous? No. Good. Moving along. So now I want you to try this one, and I'm going to come walk around, peer over your shoulders. Work at some point to see how you are doing and maybe offer some solutions there. I'm going to start by cross multiplying. So again, don't forget to distribute. So I'm going to get 3x squared minus 30. When I cross multiply the others, it will be 2x squared plus x. And remember that there's an equal sign in between those two things, so you're keeping your equation, you're creating a left side and a right side. Now when you look at all your terms there, note that you do have some that are x squared, you have an x, and you have a number. So the fact that you have x squared and x means we're going to follow this same step, which is get one side equal to 0 and then factor. I always try to focus on my x squareds. I want, in order for me to be able to factor, I want my x squared to be positive, because that's how I know how to factor, and that makes it easiest to factor. If you have negative x squared, then one of your factors is x and the other is negative x, which that gets a little bit messy. So when I look at those x squareds, I see that 3x squared is larger, so I'm actually going to subtract 2x squared from both sides. And then I get x squared minus 30 equals x. I need to bring that x over to the other side. So I have x squared minus x minus 30 equals 0. Those are not like terms, so they're not going to combine. And now I can try to factor that. Do I have factors of negative 30 that add to make negative 1, negative 6, and positive 5? So my solutions are 6 and negative 5. I should take those x values and plug them back into the denominators. Do they make x squared minus 10 or 2x plus 1 equals 0? No, be really careful with this negative 5. Some people will be tricked by negative 5 squared. But remember, negative 5 squared would be 25, not 10. So 25 minus 10 is 15, not 0. So I don't even really plug it into the numerators. All I'm concerned about there is that my denominators are not equal to 0. Okay? So they're both good. Okay. Remember, extraneous solutions is not really the norm. Okay, excellent work. We're going to do one example that is a word problem. And this is similar to a problem you have solved before, okay, in algebra. It says, in baseball practice, you have pitched 47 strikes out of 61 pitches. Okay. We would like to know how many consecutive strikes you would need to pitch in order for your your pitching average or strikeout average to be 80%. So number one thing I think you can do in a problem like this is just try to make sense of what it's saying. Okay. First of all, I'm going to focus on what they're wanting me to answer. And what they're wanting me to answer is, when will my strike percentage be 80%? Which to me makes me think my strike percentage is not 80% right now. So how would you figure my current strike percentage? $47 out of 61 pitches, right? And if someone has a calculator, do 47 divided by 61 real quick for us. Okay, so we're going to say it's about 77%. So I'm really looking right here for like a 3% increase in my strikeout percentage, or strike percentage. Okay. Now, in order to do this, we need to think logically about what's happening. And there's another phrase in here that's really important for us to make sense of. It says, set up and solve an equation to find the number x, so that's what we're trying to find, of consecutive strikes. What does consecutive strikes mean? Does that help? Strikes in a row. In a row, one right after another. sometimes in math we have to take some liberties, and we're kind of taking a liberty right here, and we're saying, you have to go up to the mound right now, and you have to just like throw strike after strike after strike. Do we understand that that might not be the case? You might go up and throw 3 strikes, and then you don't throw a strike again. Okay, but that would then mean we'd have to solve a new problem because we'd have a new strike percentage. Okay, so based off of what we have right now, what would we have to do consecutively in a row so that we could get up to 80% without missing any? Okay, because that would start our whole problem over. So what I would do is I would start with my current strike percentage, which is 47 over 61. And I just think about it. If I go up to the pitcher's mound and I throw 1 pitch and it's a strike, what happens to the top number, 47? It becomes 48, goes up 1. What happens to the bottom number? It goes up. I just threw another pitch, right? So instead of throwing 61 pitches in practice, I have thrown 62. So I add 1 to the top and I add 1 to the bottom. What if I go up to the pitcher's mound and I pitch 5 in a row, 5 strikes? What happens to the top number? Goes up by 5. What happens to the bottom number? Goes up by 5. So every time I throw, I'm saying I'm adding a strike and I'm adding a pitch. So we're going to call that X. And we're going to say our numerator will really be 47 plus X. Our denominator will really be 61 plus X. You can't just add it to the top because you're making extra throws. And you can't just add it to the bottom because you're getting more strikes. So it's adding to the top and the bottom. And we want that to be, instead of 77, we want it to be 80%. How can we write 80% as a fraction? 8 over 10? Was anybody thinking anything different? Jacob? 4 over 5? Anything different? Could have said 80 over 100, right? What's the benefit to using Faith or Jacobs? It's smaller numbers, right? It's simplified. So we could use either one. If you want to solve it with Faith, 8 over 10. If you want to solve it with the regular percentage, 80 over 100. Or if you want to solve it with the smallest numbers, 4 out of 5. You'll get the same answer. I'll go ahead and use Faith only because she said it right away. But any of those will get us the same answer. It just will change the numbers that you're using. Okay. So I'm going to cross multiply. That gives me 470 plus 10x. And 488 plus 8x. There's an equal sign in between. This time I don't have x squared and x. So now all I got to do is get all my x's on one side, get all my numbers on the other side. So when I'm looking at my x's, 10x is more than 8x. I'm going to try to keep that positive, so I'm going to subtract 8x from both sides. So that I'll have 2x over here. And then I'll want to move this 470 to the other side, so I'm going to do 2 steps in one. I'm going to subtract 470 from both sides, so that all I have over there is x's now. And then I get 18. If you used 80 over 100, you'd have 20 equals 180. If you used Jacob's 4 over 5, you'd have your answer, x equals 9. In this one, we have to divide by 2 to get x equals 9. But we should make 9 more pitches, and if we get 9 strikes in a row, our new strike percentage will be 80. So we're going from 47 over 51. We're going to add 9 to the top and the bottom. We'll be at 56 over 70, which if you do in your calculator should be 80. So there'll be maybe, I think, 1 or 2 problems like that on the homework assignment. Does anybody have any questions about what we did? Yeah, Justin?
Why is 51 plus 9?
Oh, it's 61, isn't it? Did we have 61 pitches? Yes. Sorry. That was just, I don't know what that was, why I said 51. Who knows? Thank you. Any other questions? Okay, your homework assignment is page 396, numbers 3 through 12.